Hello, everybody. Welcome to the weekly physics colloquium. We're very, very happy today to have Max Tegmark from our sister institution on the East Coast, the Massachusetts Institute of Technology. Max is very well known, of course. Many of you, someone is calling. Many of you will know Max for his work in cosmology, where he works at the interface of data and theory, the microwave background, large-scale structures, slow digital sky survey, things like that. And certainly very successful at those things. But one of the things I've always admired about Max is that he has not been afraid of wandering into other areas. And he doesn't wander just like and put his toe in and then come back. He really dives into it in an interesting way. So he's worked on the foundations of quantum mechanics, the multiverse. He is the champion of a very one of the more radical ontologies in all of the history of human thought, the mathematical universe hypothesis, which he wrote a book about called Our Mathematical Universe. He's also thought about the future of life and existential risks. And these days, he's been thinking a lot about artificial intelligence, AI, as a general thing, the threats that it comes out very naturally from work on existential risks, because artificial intelligence is arguably one of those risks. But maybe we can, instead of worrying about Skynet putting us all into slavery, we can actually put AI to work. And one of the things, I don't want to give away too much from Max's talk, but one of the things that you would like intelligence to do for you is to be a theoretical physicist, right? So can you make an artificial intelligence that acts like a physicist? That is what we're going to be talking about today. So with that, go ahead, Max. Oh, I should say, I'm sorry. We should say that we've decided that Max will try his best to keep the talk itself at a relatively compact length, and we'll save all the questions for the end. So if you have a question, note it down on your personal notepad, and we'll have a real chat session afterwards where everyone can chime in. Okay.
Great. Thank you, Sean, for that very kind introduction. A person who likes to explore a wide range of things and ask big questions. That sounds like a real perfect description of Sean Carroll to me. And I did make a pledge to myself once upon a time that if I ever got tenure, I would only work on things I was really excited about. So today I'm going to be telling you about something I'm really excited about, which is what machine learning can do for physics and vice versa. But first, I have a favor to ask you all. Please turn on your cameras, because it's much more fun for me to actually see a lot of my old friends and new friends here. So I think if you, Alvin, can turn on your camera, and you, Guochao, and you, Christina, and Tushang, and Fred, and all of you. Yes, now it stopped feeling like a YouTube video. Now it feels like I'm with you guys here. And you too, Bruce, and you too, Kyle, and Leo. Awesome. I'm so honored to see so many of you here, and great to see you, George. So let me share my screen. So I'm going to be talking about AI for physics and physics for AI. What I mean by AI for physics is, again, what can machine learning do for us as physicists? And what I mean by physics for AI is, how can we give something back? How can we take the ideas and tools and the mindset of physics and use it to actually improve machine learning? I'm going to be talking a little bit about both. I love this area, and if any one of you in the audience either has an undergrad or a grad student, or is one, and I would very much like to encourage you to come to MIT. I have a very friendly group here, and we have more broadly this new center called the Institute for AI and Fundamental Interactions, where we have a lot of faculty throughout the Boston area, MIT, Harvard, and a bunch of other universities focusing exactly on this question. So warm welcome over here. Why talk about AI in the first place? Why is there so much buzz on it about it? Well, obviously because the power of AI has grown so dramatically in recent years, right? Just think about it. Not long ago, the state of the art of trying to make robots walk, for example, looked like this. This is 5 years ago. And now let's just fast forward just 5 years. And it looks like this. Brought to you by, and so that's 5 years. Very palpable progress. Not long ago, also, of course, we didn't have self-driving cars. Now we have self-flying rockets that can land themselves with artificial intelligence. Not long ago, AI could not do face recognition worth its name. Now it can simulate Sean Carroll's face saying all kind of stuff that he never said. Not long ago, AI could not save any lives. Now we have algorithms that are as good as the best humans for diagnosing prostate cancer, lung cancer, blindness, and various other diseases. Not long ago, AI couldn't really advance medical science. Now it's just solved this decades and decades old protein folding problem, where you take as input the genetic code, the amino acid sequence, and machine learning figures out how it folds up. This is courtesy of Google DeepMind, and the final victory was declared in just before Christmas. You can see here really good agreement between the AI predictions in blue and the very expensive and slow X-ray crystallography measurements of various protein shapes. Something which I think is really going to accelerate drug discovery, drug development, and of course, not long ago, AI couldn't beat us at the board game of Go. As recently as 5 years ago, several of my AI colleagues told me they thought it was going to take decades. And then Google DeepMind took thousands of years of human Go games and put them all in the trash and developed AlphaZero that became the world's best Go player by just playing against itself for 24 hours. And now they just came out with MuZero a few months ago, where you don't even have to tell it the rules. And then it'll learn to play Go or chess or shogi. And really the most interesting thing here is not that the machine learning can crush human gamers, but that it can crush AI researchers who've spent decades handcrafting these algorithms that are now made obsolete. So with this growing power of artificial intelligence, now what can it do for us? A lot, obviously. We do physics with human intelligence, so if we can amplify it in various ways, it should be able to help us. And actually, I found now that a pretty significant fraction of my MIT colleagues in the physics department here are doing machine learning in some aspect of their work. I suspect a decade from now, it's going to be almost as hard to find a physicist who never does anything with machine learning as it is to find someone today in physics who never uses calculus. For a few more concrete examples, we're using machine learning here at MIT to better detect the gravitational wave signatures from inspiring black holes halfway across our universe, for detecting exoplanets, for detecting new physics, hopefully at the Large Hadron Collider, for studying neuroscience, etc., etc. So in addition to using these tools, can we actually give anything back? The knee-jerk reaction might be no, of course not. How is a ragtag band of physicists at Caltech and MIT going to do anything that 40,000 Google engineers cannot do? But I'm actually going to push back on that and argue that we actually can contribute a fair bit to machine learning. Not by doing exactly the same thing that Google is trying to do, but by doing things a little bit at the traditional boundaries of machine learning, where we have unique expertise. For example, let's look at some of the challenges of machine learning today. A lot of them have to do with trust and understanding. For example, people like to deploy these black box AI algorithms that they don't understand maybe as well as a physicist would like to understand things before they put them in charge of people's lives. This North Point system was deployed in courtrooms across America until people discovered that it was racially biased. And why did this happen? I don't think it was because the people who made this were racially biased. I think it's because they honestly didn't understand well enough how that algorithm actually worked. Similarly, I don't think the people at Boeing had any malice when they put this very simple automated system into the 737 MAX, but they absolutely wish they had understood it better in hindsight after they deployed it, right? And it led to the death of hundreds of passengers in these two planes that crashed. Raise your hand if anyone of you invested money in Knight Capital. I'm glad to not see any, because they deployed this very nice and shiny AI automated trading system, which went on to lose $10 million a minute for 44 minutes. Again, because they just hadn't understood well enough what it was actually doing. And even in situations where we tend to blame malice, like when there's hackers, it's actually, if you look at it a little bit deeper, again, very much the same problem of lack of understanding the system. Google, Yahoo, and Equifax, etc. Had they understood their systems better, they would have realized that there were these security flaws in them, right? So let's look at a slightly more physics-like system. So raise your hand if you ever procrastinated by playing this game back in the day. So here, there's machine learning from DeepMind many years ago, learning to play this. In the beginning, it sucks because it has no idea what a ball is or a game is or anything. It's just given as input a bunch of numbers, which represent the colors of each of the pixels here. And it's just trained to maximize its score. But after a while, it gets quite good. And after a while, if you gave a 4-year-old your iPad and then you come back after a little bit and they're playing like this, you'll be like, this kid is really smart, right? It's figured out this trick for how to always drill a hole on the left side and bounce the ball there every time. So can we understand how this system works? Has it, for example, figured out, that the ball always obeys Newton's law and goes for force-free motion and moves in a straight line with constant acceleration when it's not bouncing? Can we trust it that it's going to work every time? Well, in this case, we can answer this question because I just trained this on one of my servers in the lab. So let's look under the hood what it actually did. It takes as input, as I said, this long vector, which just contains the colors of all the pixels, multiplies them by a gigantic matrix, and then applies a nonlinear function to each one of the results, multiplies by another matrix, and does that a bunch of times. There's 867,488 tunable parameters all in all that it optimized to get the best score. Is it crystal clear now how this works? Do you trust that it's always going to work? Is it obvious that it kind of learned the physics of the ball motion? And this is completely useless, right? So this is what I want to focus on for the theme of this talk. The slogan of my group, intelligible intelligence. How can you go beyond getting something which does stuff which seems kind of smart in a black box fashion, to open up the black box and actually get a deeper understanding of what it's doing, maybe even transform it into something which is as capable, but unintelligible, so you can trust it, not because the salesman told you to trust it, but because you understand it. And some of my machine learning friends even sort of worship the mystery of black boxes a little bit and say, not only will we never understand how these things work, but we should give up on that. And maybe the mystery of it is sort of even secretly the part of the power of why they work so well. I think that's just complete nonsense and hogwash. I think that the power of deep learning comes not from inscrutability, but from differentiability. And let me explain just very briefly what I mean by that. So what does deep learning neural network ultimately do? As I said, from a physicist's point of view, it's something very simple. It's really just a function. If you feed forward neural network, something goes in, something comes out. And the example I showed you now, what goes in is a vector with a bunch of pixel colors. What comes out is some number that represents what you should do when you play a game. What's inside is, as I said, you just multiply by some matrix, apply some nonlinear function to each of your numbers, and repeat a bunch of times. So it's a function with a bunch of knobs that you can tune, right? Numbers in these matrices, basically. and some vectors you can add. And there are some cool theorems from the 80s that prove that this way of parameterizing functions can very accurately approximate any function whatsoever, at least any continuous function that we tend to be interested in, if you have big enough matrices. And what's so interesting about that is, as opposed to when you implement functions by writing code in Python or C++ or something like that, that any setting of these knobs, of these numbers, of these parameters, is a valid program. So the whole thing that you're doing just becomes an optimization problem. If you can define to the computer some measure of what good means for your function, now you tune all these knobs and you minimize it. You can, and because any setting of these parameters is valid, right? You can do gradient descent. You can change them a little bit in some direction, or compute the numerical derivative and figure out what direction you're supposed to change the knobs. You get information about how you should change your function continuously to make it better and better. Contrast that with if you were writing a program in Python or your favorite language, right? And now you're going to start continuously having the computer automatically change the program until it gets better. So it says print, and now it randomly changes the letter R to the letter F, and it says fint, and you get a syntax error. You got no information about whether that was a step in the right direction or the wrong direction. It's this differentiability, I think, which is so powerful. And this is, I think, why the human brain also has, one of the reasons, locked into this architecture for how we do our computations very much. It can, in an automated way, get better at whatever you can formalize. So let's look at this in a little bit more detail here. I want to tell you briefly about 3 papers, which are all focused on taking, as a first step, a black box where you've just trained a neural network to do something cool. And then see, can you, instead of stopping at that point, which is what Google would normally do if they're making a product, but continue on to try to understand more deeply like what you're doing, okay? Before delving into this, let me just motivate this a little bit. What made me really excited about this was thinking about people like Galileo. I'm sure when he was a kid, if his dad threw him an apple, he could catch it, because his neural network in his brain, he had trained it in a way he didn't understand to predict the parabolic trajectory of the apple pretty good, right? Dogs can do this really well also, for all of those of you who like to play with dogs, right? But what humans can do too, better than dogs, is something Galileo did when he got older. He then took this intuitive representation, much like deep learning, right, and distilled out of it a more symbolic understanding of what he had learned. And he realized that this shape that the apple moves in can be described with an equation, in this case, y equals x squared, a parabola, etc. That enabled him to communicate it with his friends and colleagues. Even when we do symbolic representation by speaking English, right? This is again something we're much better at than dogs. We take something we've learned in the kind of deep learning sort of way, and then we distill out things that give us a more abstract and deep understanding of it that we can communicate. So I want to tell you about 3 things we've done in this spirit. I want to first talk about how you can try to see if you can approximate the black box by actual equations, symbolic expressions. Then I want to talk about if you can learn conservation laws. And finally, I want to talk about how you can figure out what degrees of freedom you should even pay attention to. So let's start with the first. This is the problem called symbolic regression. And this is a paper I recently did with this gang here in my group. And the title is a bit of a mouthful: Pareto optimal symbolic regression exploiting graph modularity. So let's just unpack this in pieces. Symbolic regression, what's that? Well, if you have a table of numbers and the last column is just some function of the earlier columns, figuring out what that function is, that's symbolic regression. If the function is linear, that's just linear regression. And I think you've all done that many times in the past. You know, it's very simple. You just have to solve a system of linear equations. It's really useful too. But if it's some more arbitrary nonlinear symbolic function, this is hard. Kepler spent 4 years staring at Mars data until he was able to discover this symbolic expression. It's an ellipse, transforming astronomy. I'll show you our automated software now that solves this automatically. And it's obvious that it's hard, and it's probably NP hard actually, because if you were to just brute force try all possible symbolic expressions with n symbols in them, right, you have to try exponentially many, obviously, just like the number of passwords of length n is going to grow exponentially with the number of letters you can have in it. And very quickly, even for simple formulas like the black body formula, whatever, it starts taking over the age of our universe to try them all. So that gets to the second part of what we did in this paper, graph modularity. So what's that? We're trying to learn functions, right? Symbolic expressions. And you can obviously represent all of them as graphs, like computational graphs, like in the middle here. The one on the left side is a function that takes 3 variables as input and outputs 1. What I mean by modular is simply that graph is modular. So this example function here, if you look on the right side, is you can actually decompose it into 2 separate functions of 2 variables. And so what we discovered, which I was very excited about, was that there's actually an easy algorithm for discovering any modular structure that might exist in your mystery function, even without knowing what the modules are. What you first do is you train a black box neural network, like we discussed, to approximate the function well. And then you compute the gradients of this, and there are certain algebraic properties that will hold if it's modular, and you can recursively uncover all the modularity, no matter how much of it there is. Which means that you can take a problem where you don't know what the function is and break it recursively into smaller pieces until you can figure out what the pieces are, hopefully, and then put it all together and get the whole thing. So you can think of this as a recursive divide and conquer algorithm, where someone gives you a table of numbers again and asks, hey, can you figure out what this function is? And first you train a black box to fit it, study it, and discover some simplifying properties, which lets you reframe this as one or more problems with fewer variables, and then you recursively keep doing this. Let me show you just one concrete example to make it a bit less abstract. Suppose you did not know Newton's law of gravitation in the upper left corner here, and you just some friend of yours just generated a bunch of random values of x and of the different positions and masses and whatever, and gave you a table of numbers showing what the force was for each situation. First, we just do some automated dimension analysis, which is so simple it's boring for us physicists. And then you get something in the form over on the right here. Now, you train this neural network to approximate this, and then it discovers that this actually is a modular function, even though it doesn't know what it is. It discovers that the inputs C and D, they only appear, they get combined, and then that's the only way they enter into this. So it discovers that, and then it discovers actually the way they get combined is just they get subtracted from each other. So now it takes the C column and the D column and just replaces them by their difference. Now it has a mystery table that it has to solve with 1 fewer variables, right? Now it starts over recursive from scratch, makes the neural network that approximates that, discovers again, oh, now the E and the F variable also entered only in a very simple way as their difference. So it reduces again, and then it discovers actually now there's another kind of modularity here. This is a multiplicatively separable function. It's just a function of A times a function of the other stuff. And eventually it breaks it into small enough pieces that it's able to, by other means, figure out what they are, and then it puts it all together. Earlier, we had written the paper where we were able to only do certain kinds of modules would get discovered and only have 2 variables. But then we now have this more generalized scheme that just discovers any kind of modularity with any number of variables, even if you don't know what's in the modules. Okay, finally, to unpack this unwieldy title, what on earth is we mean by Pareto optimal? Well, I'm a big fan of Occam's razor. And in physics, generally, we value not just accurate models, but also simple models, right? That's kind of the point of Occam. So what we did was for each candidate formula that our system produced, we evaluated not only its inaccuracy on the y-axis, but also its complexity on the x-axis that I'll define for you in a little bit. There's obviously a trade-off there, right? If you make a super complicated formula, you can generally fit better. The simplest possible formula you can have is just to predict 0 all the time. That's the upper left corner, but it's not, it's very, very inaccurate. We physicists like things that are simple and accurate, which means convex corners along this trade-off frontier. And you'll see that there are 2 convex corners here. One of them is in the lower right corner, where it discovered Einstein's formula for kinetic energy, which is not so surprising because without telling it to our algorithm, that's actually what we had put into the data. But you see, it also discovered this convex corner here in the middle, mv squared over 2. So it has the same intuition. It captures a little bit of our physics intuition as to what kind of approximations are actually useful. Now, you learn about this one in high school, but you don't learn about this other one in high school, mc squared over 1 divided by v over the cosine thingy, right? How did we define this complexity? Well, we went for a trade-off, a compromise between Occam's razor, which is too vague to turn into some sort of computer code on one hand, and Ray Solomonov's definition, which is super rigorous but NP hard and takes longer than the age of our universe to compute, the smallest number of bits you would need to describe the formula somehow, and coded up a compromise which is very fast to compute and still captures a lot of the gist of what Solomonov's complexity is trying to do. So if you want to know how complex is an integer in our model, it's basically the number of bits you need to write the integer out in binary. If it's a natural number like 5/3, it's just the number of bits for the numerator, plus the number of bits for the denominator. If it's a big parameter vector, then you sum up the bits for all the different parts, et cetera, et cetera. And even though this is crude, we found it actually worked surprisingly well. So to test this, we took the 100 most famous equations from a very, very famous Caltech professor who I have a very special affection for, actually, not because I'm trying to suck up to you guys, but because Feynman is actually the reason I went into physics in the first place. You can ask me about it in the Q&A. So it was cool to get to pay some homage to him finally. So we took 100 equations from there, turned them into just basically Excel spreadsheets with numbers to see if our system could figure out what the equations were. Then we took a bunch of equations from some grad textbooks that were floating around my office, like these ones. And then we took some other equations which had various kinds of modularity in them. We also wanted to see if we could auto-discover equations, even if all we were given were just probability distributions, just this cloud of points. There, what we did was we first used the technique of normalizing flows that you can ask me about later, which is a machine learning technique that lets you estimate the probability density. And then we threw that into this AI Feynman code to see if it could guess the function. Here is how we did. The state of the art in this field has been for over a decade, this very, very nice genetic algorithm by Schmidt and Lipson, which was able to solve 71% of the Feynman mysteries and 15% of the harder ones. We were able to do 100% of the Feynman ones and 90% of the harder ones. And what we were most excited about was actually that when we threw in this Occam's razor idea, also I think got much, much more robust to noise. So we could throw in like 100 or 1,000 times more noise on our data points before we broke the whole thing. And the 3-word summary of everything I've said about this AI Feynman symbolic regression project is pip install AI Feynman, because that's all you have to type on your computer if you want to play with it, as opposed to the Schmidt and Lipson thing, which is commercial. This is just open source. Let's come back to this black box demystification quest again and look at a couple of other examples. So if you have a system where you a physical system that's doing something, one thing you might be very interested in is seeing, can you find equations of motion for it, right? That's something you can do with AI Feynman if you want. But there are other things you might also ask as a physicist. Sorry, like sneeze, for example, or ask, are there any conservation laws? And you might also ask, even before you get to that, like, what if it's a big complicated system? Maybe your data consists of images from a microscope or a telescope or something with millions of pixels. Which degrees of freedom should you even pay attention to, right? It's easy to underestimate how hard that is and how much of the true genius of a physicist goes into that, seeing what is even important to focus on. Eugene Vignery even had a beautiful essay about that, how most of the world is actually not so predictable, but we tend to take the part that really is useful and predictable and make that the domain of physics and find equations for it. So can that also be automated in some way? We call that pregression because it's kind of the thing you have to do prior to starting even symbolic regression, figuring out what degrees of freedom you're trying to just find equations for. So this is a paper I did with my grad student Silviu Marinodrescu, and it was just accepted for publication yesterday. And so Schmidt and Lipson, this paper I paid tribute to earlier, they did this really cool thing where they just videotaped a bunch of dynamical systems in their lab with a double pendulum and whatever. And then they measured the X and Y coordinates with some Python code or whatever and fed it into their algorithm and tried to figure out the equations. But I always felt that was sort of cheating a little bit, because if you look at something like this very, very abstractly, you've never learned anything about physics, and your task is to keep predicting the future from the past. Now, for you, maybe it's obvious that you should write some code to measure the X and Y coordinate of this rocket, right? But suppose you're a computer and you don't know anything about the world. Why is that so obvious? If this is an image with 10,000 pixels and 3 colors, it's just a vector of 30,000 numbers, right? You don't even know that it's representing an image. We would like to ask the harder question. If you just have some data vector evolving in time, is there some automated way to figure out what about that is actually really useful to pay attention to predict the future? The ultimate goal then is you send in a video, and it should learn some mapping from each image into a low dimensional latent space, as we call it. In this case, a mapping from an image, which is a vector then of maybe length 30,000 or whatever, into a 2-dimensional plane where you just plop down the X and Y coordinate of the rocket. And then in turn, you can use this AI Feynman technique to then from that learn the laws of motion. In this case, it was the quartic oscillator, nonlinear. This might sound like an easy problem because, again, writing some code to figure out X and Y coordinates seems kind of trivial. But let me try to persuade you that it's actually quite hard, because if you can solve it in this abstractly defined way, then you can also solve this problem, where I'm showing you the whole video through some really weird distorting lens, right? And if you want to find the simple law of motion now, you should not just extract the X and Y coordinates of anything, right? If you think about how we humans do vision in the world, actually, we also see the world kind of distorted. We infer that there's a 3-dimensional world out there, but we have this stereoscopic projection on the retina and so on. And sometimes things look bigger and smaller, and our brain sort of automatically for us represents it in the way in an X, Y, Z coordinate system sort of for us. So how can we automatically learn this without telling it anything about palm trees or rockets or anything? So this is what we implemented. We made an architecture with 3 different neural networks that we trained together. First, we made this yellow arrow and this one, which together make up what machine learning researchers call an autoencoder. You take an image and you just train a function that maps it into a 2-dimensional space or 5-dimensional space or whatever. I'm going to call this low dimensional space. the green square, the latent space. And then you may train another neural network to now uncompress this back into an image again. And you penalize it if the thing doesn't look like the original. So that part of it just tries to figure out, okay, what do you really need to memorize? What is it that's different about images? And then we also train this other neural network called U that takes two representations in a row of this, 2 points in the latent space, and tries to predict the third. You need at least two because the laws of physics are second order, so you need the past 2 frames to be able to get at both position and velocity, right? But it can auto-learn also how much of the past it needs. The catch with this is, for it to be interesting, you have to have some, bring in William of Occam here again and come up with some definition of what you mean by simple laws of physics, because you don't have to look at this architecture for very long until you realize that if you have one way of doing this, it's degenerate. There are infinitely many other ways of doing it too. It's a little bit like when Sean Carroll teaches, if you read his general relativity book, yeah, you can pick a nice coordinate system where you describe it, but you could also do some arbitrary invertible transformation of your space, and general relativity still works, right? There is nothing, if you don't insist on some kind of simplicity, there's nothing preventing this system from coming up with some ridiculously distorted representation of space, which will be nothing like the x and y coordinates that we find useful. And then it will epically fail to discover that the laws of motion are simple, even if they are. So I started thinking a bit about the sort of stuff Sean has been doing in general relativity, and seeing Einstein actually gives us a kind of natural metric of simplicity for spaces. It's curvature. If you have a mapping from one high dimensional space to another, right, you can compute the Jacobian of this mapping and take it times the transpose and think of that as a metric, induced metric tensor. This is a bit like what we do in the tetrad formalism of GR. So I started thinking about, maybe what if we just minimize the curvature somehow and see, in addition to minimizing the accuracy, we sum them up somehow and see what it comes up with. It's a little bit of a pain in the rear to do that because you have to compute first, second, third derivatives and so on. So we started thinking maybe there is a simpler proxy that sort of captures the gist of this that's easier. So in particular, if you just penalize derivatives of your Jacobian matrix, then if in the limit where the Jacobian matrix has no derivatives, it's just constant, right? Then the whole Christoffel symbol is going to vanish. There's no curvature at all. And so we tried that, and lo and behold, it actually worked quite well. We were able to. We made video series for this rocket moving in gravity and magnetic field, and then the 2D harmonic oscillator and a quartic oscillator potentially. In every single case, it automatically was able to discover this 2-dimensional latent space, and then it was able to learn actually the laws of motion by plugging it into AI Feynman. But I would be remiss if I didn't confess why this took us a whole year to solve, in the hope that maybe you can learn something useful from our failures in the beginning. So for the longest time, it was failing epically. We would take the simplest possible case where these rockets were just moving uniformly. And even then, instead of discovering a latent space where you just got straight lines like this, it would discover something that looked to me a little bit like a cat here in the middle. And like, damn it, why can't you just learn straight lines? Why can't you just learn to extract the x and y coordinates? And then eventually staring at this, it kind of hit us that this is all about topological defects, actually, because if you take a towel, if you think about this, all these images as just points in a high dimensional space, right? There's some 2-dimensional submanifold in this high dimensional space corresponding to all the images with rockets in different places. So I think of that kind of as a crumpled up towel. And then if you just drop it on the floor, your towel, to start by projecting it onto a 2-dimensional space, and then later you try to stretch it out, it's going to be all folded over on itself when you just initialize your neural network training. And then it turns out it can't uncrumple itself, because whenever you try to cross two trajectories that aren't supposed to be crossed, you hit a huge energy barrier, because that corresponds to two rockets that are actually in very different places that are being mapped onto the same place in the latent space. Now it's impossible for it to recover this. So it's like you have all these wires that are sort of repelling each other. So I started to think about this famous theorem that says that, from knot theory, that says you can't tie your shoes in 4 dimensions, proven by our topology friends. And I thought maybe we should have a higher dimensionality in our latent space so that things can sort of untangle themselves. Then Silvio and I started reading up on high dimensional knot theory, and there's a little formula, like if it's 2 dimensions, if it's like a towel that's crumpled up, then you need 5 dimensions minimum in the latent space, and so on. So we used this knot theory guidance, went to 5D latent space, and now magically it learned things great. So it ended up auto-simplifying itself into some 2D hyperplane in 5 dimensions. We could figure out that by just doing principal component analysis and see that there were only 2 principal components that were big. And then we could throw away those extra 3 dimensions now that we no longer needed them. It kind of needed those extra 3 dimensions just to simplify itself. Then we could get rid of them. I'll skip over this little part, but it turned out later we were also able to, even after this, there was a little bit of residual symmetry where it could learn a latent space, or translated or rotated latent space, or sheared. They were all equally good. But if we insisted on all of these different laws of physics being simple kind of at the same time, we could break that symmetry too, and it actually got the exact sort of rediscovered the inertial frames. It wanted a latent space that was rotationally symmetric, and so on and so forth. The last thing I want to do, and I want to leave a lot of time for discussion, so this last piece will be super brief, is just advertise that if you have some physical system that you don't really know much about, either because you measured it in your lab or you simulated something in a supercomputer simulation and you don't know if there are like useful approximations to be found there, you can also automatically look for conserved quantities. So this is this AI Poincare paper I wrote with my student Ziming Liu. And the idea is very simple. If you think of a dynamical system, then if it has, for example, 2 degrees of freedom, right, then the phase space is 4-dimensional, right? You need to specify 2 positions and 2 momenta to know this, to be able to predict the future. If there is a conserved quantity, like energy is conserved, for example, that means you're not going to have the system moving around in the full 4-dimensional space. But it has to, because there's one constraint, you're stuck on some 3-dimensional submanifold. You lost 1 dimension. If there is another conserved quantity too, then you lost another dimension and you're just moving around in a 2-dimensional manifold, etc. So if you want to know how many conserved quantities there are, just from looking at data, it's equivalent to figuring out the dimensionality of the manifold of your data. And there are a lot of techniques for doing this, but unfortunately, none of them work particularly well for these physics problems. So Ziming came up with a very clever way of doing it better. I'll skip over the machine learning details. You can ask me about it if you'd like. But basically, just given a cloud of points, or measurements of what your data vector is doing at different times, it machine learns a continuous smooth approximation of the manifold, and then we can take that learned one and we can look at it on different length scales and do a principal component of very small length scales. We just see noise. It looks fully like it has the full dimensionality. We can look on very large scales, and it's going to look like, again, just the shape of the manifold. You have all the dimensions there, but there's some intermediate range of scales where the manifold looks kind of locally flat and you're not dominated by noise, where you can see, there's 1 dimension missing or 2 dimensions missing or whatever. And that lets you extract out the conserved quantities. In the end, it gets very automated. You just plug in the data points that you've measured from your system over time and run this code, which is also open source. And you get a plot like the bottom one, which just shows the effective number of degrees of freedom of conserved quantities that it detects. as a function of the length scale. And for all of the cases here that we ran, the magnetic mirror, double pendulum, Kepler problem, etc., you see it's very obvious. The first one conserved quantity, energy. The Kepler problem, you see this curve peaks at 3. It's, of course, the energy, the angular momentum, and the Runge-Lenz vector. Double pendulum, only energy. Magnetic mirror, only energy. 3-body problem, etc., only energy. And you can ask me about this later again, how one can get equations out to describe the conserved quantities, etc. I just want to shout out one last thing here I think is conceptually kind of fun. If you think of this dimensionality as something that's not just a magic number that you derive yourself by knowing the equations, but if you think of it instead as an effective number of conserved quantities over some time scale, and maybe it depends on the parameters of your Hamiltonian also, then you can put on your condensed matter physics hat and actually start thinking about phase diagrams. Like, how many conserved quantities are there of this system, like as a function of how long time you observe it, as a function of some parameters in the Hamiltonian. We took, for example, the Kepler problem where you get an ellipse, right? And then we changed the inverse square law to be 1 over r, not r squared, but r to the power 2 plus epsilon, and we changed epsilon a little bit. Now the ellipse starts to precess, so you gradually lose that one conserved quantity, which is the angle of the principal axis, if you go long enough. You can, by looking at phase diagrams like this, discover all sorts of interesting properties of your systems kind of automatically. It turns out periodic orbits pop out, sometimes even funky properties of them that we hadn't thought about in advance. So I want to wrap up here so we have a lot of times for questions and just take a look again a little bit at the big picture. So I feel that not only can machine learning do a lot of stuff for us physicists, what I've highlighted in that department today is I think that machine learning, it's fun to unleash machine learning on whatever large data sets we have to see if they discover some interesting patterns in there that we may have missed, right? That we can then look at more carefully ourselves and see if there's something cool there. But I've also tried to emphasize that we physicists actually can add some things to what machine learning is doing, because I think we physicists tend to have a much higher bar for what we mean when we say we understand something. If we, for example, if you feel confident that the rocket you built is actually going to go to the moon and not crash on San Francisco or something, right? It's not because you did a bunch of trial and error launching. Oh, this time it crashed, so I'm going to launch it a bit farther to the left. No, it's because you figured out we figured out the laws of gravity and all that other good stuff. So we feel we really have trust in these systems. We understand them at a very deep level, and I think that kind of audacity that we have in physics, we go in and try to understand things even that people in neighboring fields think are hopeless, is something we can bring to machine learning. And in particular, I think we should set our sights on this black box of machine learning. When they have some complicated system, it's clearly doing something smart, and they've sort of given up on understanding why it's working like this and how. I've given you a few examples about how I think by using other ideas from physics, like studying the curvature functions create, or Occam's razor ideas, or not theory for math, or whatever, we can actually, in a rather also automated fashion, start a little bit in the direction of what Galileo did, right? Distilling out from this intuitive understanding that the black box has, distilling out what is actually learned in terms of maybe formulas, maybe conservation laws, or other things, and ultimately help our friends in other fields understand things better and help them make systems that they trust, because they actually should trust them, because they understand how they work. And I want to end with an invitation. I've shown you some tools that we built. We're very eager to play with them. So if you have any data floating around on your hard drive, either that you measured in your lab or that you simulated on your computer or that you know exists out there, that you think there may be cool new patterns left to be discovered in, please shoot me an email at tegmark@mit.edu. Would love to collaborate with you. Thank you.
All right, let's thank Max. And obviously, we'll take questions. We left time. I have questions, but I'm going to let everyone else go first. So I see Matthew Graham has a hand raised. So raise your hand in Zoom if you want to ask the question. So Matthew.
Hi, Max. This is very interesting. So George Zagowski and I applied Eureka to astronomy data sets back in about 2013 and looked at symbolic regression with that. And we've got a paper there where we were looking at can we recover Hartsprung-Russell diagram? Can we recover the fundamental plane of galaxies? And then also where we had more success, or I mean, we had some success with that. It depended on the data sets we were finding, we found, but was also then using symbolic regression as a binary classification technique and going into that road where, you don't know what your classifier is, but if you know what the labels are, you can use it in a sort of supervised learning sense. And so, I'm always interested in where the symbolic regression world is going for the last 5-10 years. What I'm interested about AI Feynman is how do you deal with real world practicalities like measurement error, which can often obscure or manifest as pseudo relationships, and also things like irregular sampling of time series, if that's the sort of thing you're putting in, or sparse sampling of particular quantities in some dimensions.
Great. First of all, this sounds really cool what you did. If you and George could email me some links.
Yeah, I will do.
Yeah, I would love to learn more about it, especially the last part. I would like to understand better where you use it for unsupervised learning in this binary classifier. And email me. Maybe this is something we could do together here. Because
yeah, sure.
You asked about the evolution of the field. I think the field to some extent stagnated a little bit, frankly, after the Schmidt and Lipson work.
Yeah.
And there weren't really any good benchmarks out there for people to test their codes on. And there's sort of a dirty secret underlying all symbolic regression, which is the so-called no free lunch theorem of computer science says that it should be impossible. It is actually true that if you just have an absolutely arbitrary function, there's nothing you can really do about it. It's going to look like the output. You send in some stuff and you send it through some crypto system, and out comes what just looks like random noise, right? But for some reason that we don't still fully understand, the kind of functions that nature actually throws at us in science have many simplifying properties. And that's kind of why AI Feynman works. We don't know really why. I don't think I understand why there's so much modularity, for example, in the actual functions we care about. But there is, so we exploit that. Another kind gift we get from Mother Nature is that if you think about it, the functions you use in your math and learn in school generally tend to be functions of either two variables like plus and times, or functions of one variable like cosine or the logarithm. But you basically never come across fundamental functions of 3 variables or 7 variables. They don't seem to be so, nature doesn't seem to insist that we use them very much, right? And that we shamelessly exploit in this also, because it's exactly for that reason that this whole scheme I showed you works. So shamelessly exploiting those kind gifts that nature has given us, I think, is a core reason why this has all helped. And of course, also just machine learning, the differentiability, because the Schmidt and Lipson doesn't really use neural networks. In terms of the question you asked about noise and lack of robustness, the first version of our paper, the one that we published in Science Advances, was in fact not particularly robust to noise. That's why we went back and spent all this time putting in this Occam's razor stuff. which helps enormously. You know, the basic problem always with noise happens if you overfit it, right? If you make a model that's so complicated that what the model has basically done is just kind of memorize the data set, which makes it perform absolutely terribly when you now try to apply it to some data it hasn't seen. So since this Occam's razor punishes exactly that and forces you to make the simplest model you can that still gives decent results, it becomes much more resilient. So a lot of work left to be done, but I feel that you shouldn't be scared of noise. This is something that can absolutely be handled with this sort of information theory-based Occam's razor strategy.
I mean, data that is not exactly correct has often been a problem for real theoretical physicists, not just for artificial ones. So we have to cut it some slack. All right, David Stevenson, I think, is next.
Yes, you mentioned several times your fondness for William of Occam. It would seem to me that in some sense, physics is defined as a subset of problems that share simplicity and are reductionist. And if you look at the full spectrum of science, there are a lot of very important problems that are not like that. Even in astronomy, but especially in earth science, and even more so as you go to biology. It's my impression, certainly in the things that I've been involved in, that Occam's razor doesn't work. And the reason is that the number of degrees of freedom, the complexity of the problem is just too great. And of course, you can go even further and get to things like economics, where even experts will disagree with each other at a fundamental level. So my question to you then is, are you defining for yourself an area to play in where you can make progress, or do you actually aspire to something grander?
So I think you beautifully captured actually a core part of Eugene Wigner's argument that I alluded to earlier there. He says that what physicists have really done when they claim that we claim that we can describe the world so well is we've taken the tiny fraction of stuff which we actually can describe and call that physics, and everything else that's so complicated we can't deal with it, and said, oh, that's just initial conditions, and that's not our department. So with that humility in mind, I think that the whole goal of this research program that I've been describing for you is not to try to solve all problems, but rather to see, can we do more than nothing? Are there some problems out there that when you actually apply Occam's razor, they will actually yield? And to that, I think the answer has turned out to be a resounding yes. And that's the places where I want to start. You know, it's clear that we're generating just exponentially more data over time now, and it wouldn't be fair to those of you who are grad students just to have you spend your entire life just staring at that. So it's very nice if we can automate a little bit of this task of looking through massive data sets and see if there are interesting patterns there that we can then all follow up on.
Okay, I think that Alexander Zlokapa is next.
Hello, thanks for the talk. I had a question about, I really liked your analogy of, what a human does differently from a child or you mentioned a dog. But as a physicist, one thing we do also is create experiments, right? That then try to highlight what we don't understand. I was wondering if you thought at all about, in some sense, scoring what data would be most useful to advance, since like a physicist isn't just doing a symbolic regression, but in terms of like a Bayesian acquisition function or other idea.
Yeah, that's another really fascinating set of ideas I did not talk about here. I'm very interested in it and have done a bit of work on that we haven't published yet, but because everything I showed you now was basically taking the data set as given, and then you just try to see if you can make sense of it. But what you do as an experimental physicist, or for that matter as a young child also, right, is you put a lot of thought also into what data should you go gather. You know, should you go open that cupboard and see what's inside it, or should you do this other thing? And it's pretty clear that there's a method to the madness for all of you who do have children, right? We can curiosity seems to have a lot to do with trying to figure out what data you should collect. That's most likely to help you make better predictions in the future. And I just think I just basically want to give an upvote to what you said there. I think this is a very interesting area to do more work.
George Georgovsky, I think, is next.
Yes, that was really nice, Max. Two quick comments. The first one is that we're brainwashed as physicists to look for analytical expressions for laws of nature. But we know that lots of phenomena are simply not analytically describable, not solvable, starting with unrestricted three-body gravitational problem, never mind more complex stuff. So then it really becomes the issue of finding useful analytical approximations to the phenomena that we know are not describable analytically. That's one comment. The other one is
I've been working on that one
first,
actually, just before we go to the next one. So completely agree with that, of course. And indeed, it's one of the reasons we had fun doing the three-body problem in the AI Poincare paper. One of the things I find that I really like about this modularity discovery is that it actually works even if you don't know what the functions are in the modules. You might still realize that this complicated function of 9 variables can actually be broken down into, here you take this other unknown function of 2 variables. There is no, it's not the Dresden and Rishik's list of book of functions, right? But you can study it. Again, breaking the heart, you might still find some guidance from this, in other words, for how to break things into more digestible pieces. Back over to you for part 2.
Yeah, I've been working with collaborator Pablo Moscato from University of Newcastle in Australia. He's like a world-class expert on memetic algorithms and we've been using Eureka to explore this kind of stuff. So we run into the question of ambiguity, that of course you have a huge freedom in choosing the libraries of functions that you'll be using. And then you have a huge freedom in choosing the complexity criteria for your formulae and balancing them against the traditional information criteria from probability and statistics. So I don't know if you have any practical advice on that front or opinion of how to go about it.
I certainly don't have any glib answers for like, this is the way to do it, but I do have a lot of painful and also sometimes fun experiences from working on this now for quite a while. And one sort of meta takeaway I've had is that sometimes you can get a long way with even relatively crude measures of simplicity, and it doesn't matter so greatly exactly what you pick. I mean, the ultimate example for that is Occam's razor, after all, right? If you agree that Occam's razor has been helpful in the history of our field in the past, getting rid of epicycles or ether or you name it, right? Then that's an incredibly vague measure of complexity, really, right? No one even had a formula for what's the complexity of an epicycle, but it still was a kind of, it still sort of pushed you in the right direction. What we picked here was just basically that we implemented was just something that was very fast to compute and tried to capture as much as possible this idea from algorithmic complexity theory of how many bits you would need to describe the formula. And also the idea with curvature, you know, as a measure of penalizing complexity of a neural network, there may very well be better ones. But we found that this one already worked good enough in our case for it to be able to find the things that we physicists actually wanted. I often wonder, you know, what's going on like in your brain, George, or all of you got yours brains actually, because we humans face that same problem every day, right? We take in megabytes of information through our senses every second. The vast majority of it we delete. Some of it we choose to keep. That's like in the regression framing, right? What algorithm does your brain use for that? You also have an internal representation of the world around you, right? How did you pick that one? That corresponds very much to the latent space that I mentioned in the progression from. How do you pick that? And what's your? It seems pretty clear that evolution has some sort of algorithm that makes our representation of the world as simple as possible, because then it becomes easier for us, cheaper for us to compute what's going to happen next, right? But what is it actually doing exactly? I honestly don't know. It would be interesting to take your question also and turn it on ourselves and see if we can say anything more about what it is that we do when we pick out how to represent things. It's worked well for us physicists throughout history, right? So maybe we can learn something from that going forward.
All right, Harvey Newman, I think you're up.
Thanks. Well, so first, when I heard David Stevenson, I was agreeing with him, and then I used the word turbulence. But then using the word turbulence teaches you a lot of things. So in systems which have a huge number of degrees of freedom, it doesn't mean that you're helpless. And so what you showed, Max, was actually a pointer to some of that, where you showed that on different scales, there's order and simplicity. And sometimes in high dimensionality problems, part of the problem is to understand all the relevant scales. Doesn't mean that you come up with an analytic function. So if I think about turbulence, as computation progressed, finally people were able to deal with, let's say, very high Reynolds numbers and find coherent modes of oscillation in the wake in fluids and stuff like that. And so there was a low dimensional behavior that emerged from a very complex system. So it seems to me you have a tool to explore and to characterize multi-scale problems and find scales which are not intuitively obvious.
Yeah, if you can email me, I would love to continue this conversation and see if there's actually something concrete we could collaborate on here, because turbulence is one of the areas where it really seems like there could very well be even more. There could be plenty of use of things like this. And more generally, effective field theory itself is very much about this also. Renormalization is also very much about this. You have some system with very many degrees of freedom, and then using physics intuition, you come up with some renormalization scheme or whatever and say, well, let's just let's ignore the UV, for example, and just focus on the low energy if it's renormalization, or focus on some other degrees of freedom that matter. Or if you're looking at fluid mechanics, there's a wave. Instead of focusing on every atom in the ocean, you just focus on that wave and its wave number. And now you basically have something which you can predict quite well, kind of on its own. I'm very interested in concrete examples of problems like this that we could unleash these tools on. And I could easily see it being useful not only for discovering sometimes new approximate formulas, but also for actually accelerating the numerical supercomputer simulations we do. There's already a big trend in computational physics, as many of you probably know, in many areas, where to try to use machine learning to speed up what you're doing, right? In many fields, like, so Sean, for example, you've done a lot of work in cosmology, right? Instead of having your universe and dividing all the voxels, making into voxels, where every voxel is the same size, it's much more smart to have much more compute powers to zoom in on smaller voxels where things are happening rapidly and pay less attention on things elsewhere. This has also been transformative in general relativity simulations that Sterl and others here undoubtedly know way more about than I do. So instead of having to always handcraft these kind of algorithms, could we use some of these ideas that you're mentioning here to auto-discover them and be able to simulate things with just as high precision, way, way, way faster?
Okay, Laura Delise. You have to unmute yourself. I have to let you unmute yourself. There we go.
Thank you. Yeah, thanks. That was a very interesting talk, especially for people with a background in machine learning. I was curious, you mentioned a ProPublica study at the beginning about bias in the court system and people that are being condemned with different levels of gravity depending on their race. I was wondering if you see bias in your work and how it could be at play, or on the opposite side, do you think that your work is immune to bias because you're just trying to recover physical properties of the world?
Excellent question. I'm absolutely not offering you any sort of easy fix for bias. So I think it's very important at any specific system, for any specific system you have, to really ask this question that you're asking: is it biased? Now, a key point to take away from this is that very often the problem occurs because people just didn't understand the system well enough, right? This North Point system, what it was doing was taking a bunch of data about people who were up for probation decisions, and then it would recommend whether they should go on probation or stay in jail. They had explicitly said that it cannot take as input race. So they figured, okay, well, then no problem, right? But had they understood the system better and not just treated it as a black box, they would have realized that how the system actually worked was it was able to, from other data, in this case, figure out very good proxies for that and still come up with very, very biased things. So I'm not offering any kind of fix but for everything, but I really do think it's true that getting a deeper understanding of systems is really valuable. And I would make a stronger statement. Before we put any machine learning systems ever in charge of decisions that actually affect people's lives, we should insist that we actually understand how they work. We shouldn't just trust them again because some sales rep says, oh, trust us, or this is really shiny and fancy and uses machine learning. We should only trust it because it's earned the trust, because we understand how it's working and we're okay with that.
Gabe Salmon?
Thanks for your talk. I wondered if you could speculate further on the topic that's already been brought up, which is like attaching to existing notions of coarsening versus inventing new ones. So, I mean, other people have
existing methods of something.
Notions of coarsening or coarse graining.
Coarse graining. Okay.
Yeah. So, I mean, other people have explicitly used the word renormalization group trying to understand observed empirical behavior of these neural networks. And I wondered if you could give a little bit of a meta comment philosophically on when do you need to invent new ones appropriate for the domain in question, or we can attach to existing notions as appropriate.
So let me just make sure I captured your questions. You're asking it about coarse graining and how to automatically figure out what sort of coarse graining makes sense, and also the relations between this and the renormalization group flows that we love in physics. So very interesting question. First of all, it's quite clear that a deep neural network acts a fair bit can act in some contexts quite a bit like renormalization group, where the first layer, picks up on maybe some small scale features and then gradually aggregates the higher and higher features. It's a little bit like renormalization when you maybe go, in this case, to larger scales. But the machine learning case is a generalization of what we do in physics, because in physics, usually we assume, okay, the Lagrangian of our world is translationally symmetric, so we can go into Fourier space, and we kind of already know from the get-go that if it is like that, then convolutional neural networks are useful because they basically leverage translational symmetry by going into Fourier space or something, or wavelet space or something along those lines. But a deep neural network can do something very different, which is more general and is not necessarily picking out large scales versus small scales. It might take, an image of a camera on Hummels and deciding to only pick it out, what are the coordinates of the eyes and the nose and the ears, do face recognition, or something much more general like that. So it's a very interesting field, and but a lot of controversy in it too. Another area I think you highlighted here, where I think physicists really have a lot to teach the machine learning community by taking the work that's been done in physics and seeing how much of it can be translated.
Okay, I'll take my privilege as the host to ask the final question. Max, you started with the example of Kepler, which is an obvious one, right? A classic. But we think that what Kepler did was great, but he found some algebraic equations, and it wasn't until Newton came along and found some differential equations that we had an underlying dynamical theory. Is there any conceptual difference between looking for algebraic equations and differential equations in your approach, or is it you can do just as well either way? And does the computer decide which one is the best description?
Yeah. Good question. You decide, actually, if you think if you want to look for algebraic equations, then you could, for example, just take, suppose you have you put in the list of variables that you think might be algebraically related, and then you see if it finds something. If you think there might be differential equations lurking there, then, for example, if you have a dynamical system, right, with some degrees of freedom evolving over time, what you could do is you could just make your own little estimator of not just of the derivative vector of the point in phase space and second derivative vector or whatever, and then ask the system if it can find some algebraic relationship that relates the derivatives of various orders and the value. Or if you think there might be a partial differential equation there in some fluid dynamics or whatever, right? Then what you could do is take your data again, build some estimators yourself of the various partial derivatives, and then use the system to see, can it find some algebraic relation between these, which if discovered would actually constitute the partial differential equation. So there are many ways you can deploy these techniques, but you're ultimately the boss.
I like that. I like being the boss. All right, that was great food for thought. Thanks very much. Let's thank Max again.
Thank you. Thank you. It's great seeing you all. And
thank you for staying up late while you gave us a talk.